So continuing with limiting reactant. Here we have a different ammonia synthesis using 2 moles nitrogen monoxide, 5 moles hydrogen gas, and getting 2 ammonias and 2 waters. So if we were to start with 86.3 grams of nitrogen monoxide and 25.6 grams of hydrogen, let's find the theoretical yield. So we're given grams and we want the theoretical yield of ammonia. Ammonia is NH3, which it tells you in the problem. So here we're given grams and we want ammonia in grams. So we gotta go from grams to grams. The first thing we do is we make sure we have a balanced equation. Here we do, because I didn't tell you it wasn't balanced. It won't hurt you to double check. Now, which reactant would you like to start with? It doesn't matter. Let's start with the first one. All right, that works. So we have 86.3 grams nitrogen monoxide. Can we get directly from grams of nitrogen monoxide to grams of ammonia? No, we need to go through what quantity? Moles. All right, so let's go from grams to moles. Let's calculate our moles. Nitrogen monoxide equals 1 mole. So that's what? 14.01 plus 16. So right at 30. 30.01, depending on how you want to round. I tend to like 2 decimal places on my molar masses. Cancel the units as you go so you know where you are. Now, we are now in moles of nitrogen monoxide. We want to get to ammonia in grams. Where should we go from here? Anybody remember? We have moles. Next, we go to our balanced equation, and we're going to switch. So our balanced equation here is on 2 lines, but according to our equation, how many moles of nitrogen monoxide do we have? 2. There they are, okay? And we want ammonia, so that would be NH3. How many moles of ammonia are in our equation? 2. Even though they're the same, it's not a wasted step. Okay, so now we have moles of ammonia. Our question is asking us to find grams. So we just do molar mass again. We know that 1 mole of ammonia, that's going to be what, 17.04? Is that right? 14.01 plus 3 times 1.01. Yeah, 17.04. 17 is fine if you want to round that way. It's okay. So now let's calculate it out. Now remember, I'm bad at using parentheses, so I do my divisions and hit enter each time. I'm going to get right at 49 so far. Are we finished? No, because we're halfway finished. We also have 25.6 grams of hydrogen. So we need to figure out how much ammonia that would make, because we don't know which one we're going to run out of first. So let's play that game. Hydrogen, 25.6. Grams of hydrogen. So this is H2, so 2.02 is what I'm going to use. So always go from grams to moles. If you're not sure where to go, get to moles, and then a whole variety of options opens up. Now that we're in moles of hydrogen, can we get to moles of ammonia? Yes, we do that by looking at our equation. Our equation tells us that how many moles of hydrogen do we have? 5. And the moles of ammonia are still the same for both of these calculations, so we still have 2 moles of ammonia, and ammonia still weighs 17.04 grams. Moles of H2, cancel out the units as you go. Alright, divided by 2.02 divided by 5. Alright, 86.4 roundabout. 86.4. Now what do we do? Which one's the right answer? The smaller one, yes. The smaller one, the one we run out of first. So this one is, does the question ask us to find the limiting reactant? No, so we don't have to write that down. If you want to get in the habit of it and you want to write the limiting reactant is NO, you can. But always on these problems, look at what the question is asking. Make sure you answer all the questions. Turn the page. Couple more of these, then we're going to switch. Okay. When you get titanium metal, this is, look, it tells us the equation is balanced. Thank you, problem. So here we have 28.6 kilograms of carbon is reacting with 88.2 kilograms of titanium. This now tells us how much titanium is produced. All right, now, this question is asking us 3 questions. Find the limiting reactant, find the theoretical yield, and calculate the percent yield. So we need 3 answers before we're done with this problem. The equation is already balanced. Let's start with one of our reactants. Which one would you like to start with? Carbon it is. Okay. 28.6 kilograms of carbon. Can we go to moles from here? No, because we need to be in grams. So we got to be able to get to grams. And here we'll put carbon on all of these so we still keep track of what our substance is. Now from our periodic table, carbon is, I'm going to use 12.01 grams of carbon for 1 mole. Now we're in moles of carbon. Where should we go from here? The equation, yes. So our equation says we have 2 moles of carbon. What is our product that we're looking for? Titanium, yes. And how many moles of titanium are in the equation? Just 1. If there's nothing, you can assume it's a 1. So if you like to write 1s, do that. If you don't, don't. Okay, so now we have moles of titanium. The question is asking us for kilograms of titanium. So we should go back to the periodic table and use our molar mass. 1 mole of titanium is 47.87 is what I'm going to use. So 47.87 grams of titanium. But we are not done because it asks us for kilograms. So here we know that 1,000 grams is 1 kilogram titanium. Keep track of it. There we are. Yes, the 1,000s do cancel out in this case. So let's, well, I can't push buttons. All right, who has an answer? 57 kilograms. That works. 57 kilograms, yes. I didn't push buttons right. I put 26.8 instead of 28.6. I was like, that doesn't seem right. All right, are we finished? No! He's asked us to find the limiting reactant. So let's do this whole thing again. This time with 88.2 kilograms titanium dioxide. Well, it's actually titanium 4 oxide. All right. So let's go from kilograms to grams. For me, the second calculation always goes much faster because I don't have to add up as much. We are going to need a new molar mass though. All right, so titanium, 47.87. 79.87, roundabout. 79.87 grams are gone. Now we have moles of titanium 4 oxide. So we go to our equation. How many moles are in the equation? Just 1. And then moles of titanium, you can kind of get from the equation, or you can get from the problem that you just did. It's still 1. It's not a wasted step though. And then the rest you can copy from the first part of the problem. 47.87 grams. Go on to kilograms. Okay. Let the calculator do the hard work for you. Nope. If you can push buttons, which I'm not very good at. Here I got 52.9. Close. Okay? All right, we can start answering these questions now. The problem is asking us to find the limiting reactant. What's the limiting reactant here? Yeah, it's the titanium oxide there. What is the theoretical yield? Yes, it's going to be the lower one. So if you want to write it right here, theoretical yield, 52.9 kilograms titanium. Either way, just put it on there where it's obvious for me to see it. Now it also asks us for the percent yield. We haven't done this in a little bit. So the problem tells us that we made 42.8. So it's always actual over theoretical times 100. We should never have more than 100% here. So how much did we actually make? 42.8. The problem gives us that answer. The problem will always give you the answer there. Give you the actual one. 42.8 kilograms. Our maximum amount that we could make, 52.9 kilograms. Those go away. Times 100 is, I'm behind, divided by 52.9 times 100. 80.9%, 81%, around there. 80.9%. Now we have answered all three questions. Next, iron 3 oxide reacts with carbon monoxide. Here's the equation. They went ahead and balanced it for us. Isn't that nice of them? I'm not usually that nice. It contains 22.55 grams of iron 3 oxide and 14.78 grams carbon monoxide. Here, the question is asking us for something that's a little bit different. Once the reaction has occurred, as completely as possible, so once we run out of one of these reactants, how much excess remains? So here we're not going to products. We still need to figure out what we're going to run out of first. In this case, there's a couple of ways to do it, but you can pick one of your, I usually like to pick one of my products so I can figure out what my limiting reactant is. So let's see here. Let's figure out, let's start with this one. Which product would we like to use? Nobody wants to pick. You can pick iron or you can pick carbon dioxide. I'm gonna pick iron because it's easier to calculate. Fe2O3. All right, so same process here. Okay. Let's add this up. We need a molar mass. All right, 55.85 times 2 plus 16 times. I got 159.7. All right, 159.7 grams Fe2O3. Equals 1 mole. All right. We have picked a product. So we chose to go with iron. We don't have to do molar mass here. We just need to figure out which one of these is gonna run out of first. So our equation says 1 mole Fe2O3, 2 moles of iron. All right, how many moles of iron do we make? 22.55 times 2 divided by that. 0.282-ish. Yeah. All right. So let's work with the other one. And carbon monoxide is 28.01, somewhere around there. It doesn't matter which product you pick, just pick the same, just use the same one for both of these. So we're doing iron. So here, according to the equation, 3 moles carbon monoxide gives us 2 moles of iron. So what do we get? 14.78 times 2 divided by 28.01 divided by 3. 0.351. Okay, so now we can figure out which one is the limiting reactant. Yeah, Fe2O3. Okay, so that means our excess reactant here is carbon monoxide. The question is asking us what mass in grams of our excess reactant remains. So the way that I do this, again, it's different than how the book teaches, but I like to use the same sort of process. Okay, so we know that our excess is here. So we've got our molar masses. So we can do, we know that, let's do it this way, because we can do it in one calculation. Now that we know which one of these we run out of first, we're going to run out of this one. Let's redo our calculation here, starting with the iron. We already know the molar mass, we've already done the hard work, is 1 mole. Alright, of Fe2O3. Now in our equation, we use 1 mole of Fe2O3 for every how many moles of carbon monoxide? 3. Good. So how many moles of carbon monoxide do we actually, this is how much we use in the reaction. Times 3. I don't like these problems very much. I don't like to ask them. They may show up on the homework, but they take too much time and space. Okay, so we are going to require 0.424 moles of carbon monoxide in this reaction. Now we get to do another step. Again, that's why I don't like these problems. How many moles do we start with of carbon monoxide? However much this is. We've already done the calculation. You can do it if you want to If you want to rewrite it, great. If you don't, don't. So 14.78 divided by 28.01. So if you want to get answers there, you can. So we're starting with 0.528. 0.528 moles carbon monoxide. But we only used this many. 0.424. And I'm about to run out of space. So when we subtract that, we get 0.104 moles. The problem asks us for grams, so now we get to go back the other way. 1 mole, 28.01 grams. Wasn't that ridiculous? 2.91 grams carbon monoxide. Odds of me putting anything like this on the test, very slim, because it shouldn't take you 10 minutes to work a problem. If it takes me that long, it's probably going to take you longer. All right. Last one of these. We're going to take this all the way to completion here. This is telling us all we want to know is the percent yield, and we are starting with how many grams? 10.65 grams of hexane reacts with, look, this says excess oxygen. So do we have to do a limiting reactant? No. Yes. And this is how much carbon dioxide we're getting. We want to know the percent yield. What do we have to do first? We got to balance this equation. That's right. So I need my pencil. Balance carbons first. 6, 6. Hydrogen second. 14, 2. Oxygen's last. 12. Plus 7 is 19. Okay, so we have 19 over 2. That's not good. How do we get rid of it? Multiply everything by 2. So that means this was a 1, it now becomes a 2. 19 over 2 becomes 19. 6 becomes a 12. 7 becomes 14. There's a reason I use a pencil here. Balance the equation. All right. We don't have to do a limiting reactant. We only have one reactant here. So 10.65 grams C6H14. And what product are we looking for? According to the question. CO2. Yes. So first thing we always do is we go to moles. Gram C6H14. Oh, 0.01 times 6. 0.01 times 14. I got 86.2. Yours may be a little bit different depending on how you round. Grams, and that equals 1 mole C6H14. Now, where do we go from here? The equation, yes. How many moles of hexane are in the equation? 2. How many moles of carbon dioxide are in the equation? 12. Big number. And then now that we've gotten in carbon dioxide terms, this is giving us grams, so we know we need to go back to grams in order to calculate a percent yield. Because in a percent yield, our units have to cancel out. I already forgot how much CO2 is. I think it's 44. Yeah, there we go. 44.01. That's what I'm going to use. Okay. After what we just did, this should be very easy. Doesn't take up much space at all. All right, how much did we produce? Or how much can we produce? Theoretically, we can make, I got 32.6. We'll say 32.62, I guess, since it gave us 2 decimals there. So this is our theoretical yield. The question is asking us for the percent yield. How do we calculate that? Actual over theoretical. Actual over theoretical times 100. So our actual we get from the problem, 23.75 grams. We could have made up to 32.62 grams. Multiply that by 100. Times 100. 72.8%. If you want to round to 73, that works. If you want to go 72.81, that also works. That's the final answer. Put a box around it. Circle it. Write it as a sentence. Whatever your preferred method is. All right. I don't have a whole lot of time.